All right, so in the last video we talked about how the temperature of a reaction affects the rate constant. All right, and the reason that changing the temperature affects the rate is that you can explain that through this Maxwell-Boltzmann distribution. When you've got reactants that are at a higher temperature, a higher percentage of their particles are going to have enough energy to be at or above that required activation energy, which we could represent with that dotted line right there. All right, so there's some mathematics that go behind this. It's not, this is kind of a qualitative description, but like if we were to say what percentage of those particles would have that that amount of energy. All right, so let me get my notes here. All right, so the equation that would represent this percentage is the following. All right, F equals e to the negative EA over RT. All right, so some of this should look, so first of all, what does F represent? F is going to be the fraction of molecules with sufficient energy to react. All right, so E, hopefully you recognize that from your mathematics courses. EA, that's the energy of activation. That would correspond to that energy that is required. R is the gas constant, and T is temperature. All right, and one thing about this, when you're doing these types of equations, you are gonna have to use Kelvin here, because obviously we don't want negative temperatures for some and positive. Putting Kelvin makes temperature an absolute scale, and that's why we would use it. So just to give you a sense of how this would work, I just showed E to two negative numbers. All right, this is to a negative something with a smaller denominator. This is to a negative something with a larger denominator. All right, and I just showed what these numbers would be, and you can notice that if you have a larger denominator, which would correspond to a case where you had a higher temperature, all right, you would end up having a overall higher number, all right, and that should make sense, all right. We know that the higher the temperature, the higher the fraction that we're going to have above this certain line, okay. So as we said before, it wasn't just the amount of kinetic energy. There was also this part of reacting where the reactants had to have the right orientation. All right, and there's this Swedish chemist named Svante Arrhenius, and he connected those in this equation. This is called the Arrhenius equation, and part of it should look familiar. All right, so what he said is that the overall rate constant is going to be A times e to the negative energy of activation divided by RT. All right, so hopefully you recognize that this part right here is just this right here. So this part of the equation is the part that shows the portion of the molecules that have that required activation energy. All right, what this A is an expression which is called the frequency factor, which shows the portion of the molecules that have the correct orientation. All right, so essentially that for some reactions you have tighter requirements for the correct orientation. Sometimes you have looser requirements for that orientation, and that would show up right here. All right, so you're not responsible for how these equations right here got derived, but I do want to point out that at least this equation right here is in the data booklet, so it's available for you if you need it. All right, so what can we do with the Arrhenius equation? All right, so at first when you look at this, it doesn't offer an immediate way to calculate the energy of activation, because there's actually two things in this that we don't know. All right, so just going through some of these things in the equation, what things have we figured out ways to calculate and what have we not? All right, rate constant. Could we figure out rate constant? All right, yeah. When we do the original equations, if you go a while back, All right, remember when we ran these things at the different concentrations, we were eventually able to calculate rate constants once we knew what the rate law was. All right, so we do have a way to calculate. We do have a way to calculate K. All right. What about R? R is a constant. All right. What about temperature? Temperature is the temperature that we're measuring that rate constant at. So we know this part, and this part. But we don't know what the energy of activation is, and we don't know what this A is. All right. But there's a way that we can figure this out. There's actually two ways we can do this. All right. So first of all, there are two unknowns, A and the energy of activation. And if we only have this one equation, we don't really have a way to figure that out. One way that we can do this, though, is what if we take the natural log of both sides of this? We would end up getting ln of K equals the negative activation energy divided by RT plus ln of A. And what I'm going to do right here is I'm just going to rewrite this in a way so it looks maybe a little bit more familiar. All I've done is I've broken this up to say, it's this times 1 over T. All right, and that's so that it looks a little bit more like a Y equals MX plus B type of format. All right, so hopefully you recognize if we were to take this, let's say that we were to run this reaction several times at different temperatures. All right, at each temperature we could calculate its rate constant K. All right, we could also plot that versus 1 over T at that particular temperature, and according to this equation, the point where it runs into the y-axis, or our y-intercept, would be ln of A. All right, so we could mathematically solve for what A is, and the slope of this line would be negative activation energy over R. Since R is a constant and we can calculate the slope, we could then calculate what the activation energy is. All right, so that's one way that you could do it. But I do want to point out that there is, and by the way, that's just some notes I made to myself. There's nothing important behind that. There is a way that we can do this non-graphically. All right, and that is to simply say that we're going to measure K at two different temperatures. All right, so if we measure K at two different temperatures, we're going to have two different Ks, and we're going to have two different temperatures. All right, and what we can do is subtract one equation from the other. All right, I do want to point out there's another way to do this. If A is going to be the same no matter what the temperature is, so you could rearrange this equation to say blah 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 equals ln of A. You could do the same thing over here, and since after you rearranged it, since ln of A here would equal ln of A here, the things that you rearranged would equal each other. You would end up getting the same thing as what you do here, which is when you subtract the two equations from each other. All right, ln of K1 minus ln of K2 would equal this right here minus this right here. All right, and if you clean this up, you would end up getting this equation right here. And I actually want to point out that I should have cleaned it up a little bit more, because on this side right here, you would get you could get ln of K1 divided by K2. All right, and so again, you would know what the constants are. You would know what the temperatures are. You would know what R is, and this would be the only thing in this equation that you would not know. All right, and so again, the reason that this works is that by doing this, by subtracting these two equations from each other, you end up getting rid of one of the things that you don't know, and so that leaves only one unknown in the equation, and we can solve for something if we only have one unknown. All right, so that's it for this video, and we're going to move on to talking about what we can do with these rate laws.